Optimizing arterial stents, a multiphysics approach to improving cardiovascular healthcare. Meet the team behind Arterial Stents Reimagine, Arterix, not to be confused with climbing and hiking gear brand Arcteryx. My name is Riya, and I am an engineering physics and society student. My interest in this project comes from my own experiences from getting a heart procedure done.
My name is Gursimran, and I'm an engineering physics student. Heart disease is the leading cause of death in Canada, and through this project, I want to contribute to helping Canadians as an engineer.
My name is Balkwill, and I'm an engineering physics and biomedical engineering student with a minor in nuclear studies. My passion for this project comes from a deep desire to use engineering tools to help patients in our Canadian healthcare system.
Imagine a device created to restore blood flow in a blocked artery, but instead of working with the body, it disrupts it. That's the challenge with current arterial stents. While they are highly effective at reopening arteries, many designs fail to replicate the natural behavior of blood vessels. This causes disturbed flow, increased stress on arterial walls, and long-term complications like clotting and tissue damage. But first and foremost, well, what is a stent? Now, a stent is a small expandable mesh that is inserted into a narrow artery to store both blood flow and provide structural support. But the key issue is that arteries are not rigid. They are elastic, active, and constantly interacting with blood flow. This leads to our research question. How does stent geometry and material affect blood flow, and how can we design a stent that better mimics natural arterial function? Take a look at this poll. What do you consider to be the most crucial factor in stent design? Elasticity, radial strength, the conformability of its shape and structure, maybe even the friction coefficient of the stent? Well, the real answer is all of them. Arteries are small, delicate, and crucial to maintaining, well, life. And in our stent design, we made sure to focus on all these factors at hand to create the most biologically adjacent stent there is. Our goal was to optimize both the structural and fluid performance of the stent, minimizing disruption to flow while maintaining strength needed to support the artery. Here is how we did it.
Our approach. Our first steps were discovering how to accurately implement and improve current stent features into our design. This was done through conducting initial research, which we discovered the most feasible materials were stainless steel, cobalt chromium, nickel titanium. We further understood that the type of material was a hard constraint, as it must be safe to last a long time in the body. So we decided to investigate how we would optimize the geometry of the stent, and these became the two primary factors of what to play around with the flow efficiency, friction, and the structural response, which is the stress and strain, being our metrics to measure performance.
To investigate this, we used the Fluid Structure Interaction Multiphysics tool in COMSOL to capture the interaction between the blood flow and the mechanical behavior of the stent and artery. We decided to use a 2D axisymmetric model and make the assumption that the artery is completely straight. We built the arterial wall as shown, and defined a custom material to have a similar Young's modulus, Poisson ratio, and density as human arteries do. This was assigned to the solid mechanics physics module. The stent model was then imported and placed inside the artery. This would be the component that we could modify later. It had an assigned material that could be changed and was also assigned to the solid mechanics module. The last domain was the lumen of the artery, which is where the simulated blood flows. This was assigned the linear flow physics module, and one assumption we were making was that the blood had linear flow and no turbulence around the stent geometry. A Boolean difference was added between the stent and fluid flow domain to help with later computations. The deformation domain, where the mesh would be moving, was set to be the boundary between the arterial wall and stent and the fluid flow domain. This way, the pressure of the blood would have an effect on the solid. For the stent and arterial wall, the structural constitutive equations were applied. They govern the relationship between stress and strain, deformation, and viscoelasticity in the artery and stent. All of their initial displacements were set to 0. We modeled blood flow using the Navier-Stokes equations to have pressure-driven laminar flow through the artery, with velocity and flow rates governed by relationships similar to the Poisson equations. We used the time-dependent blood pressure function in our inlet condition to simulate pulsatile flow, hence mimicking the effect of a heartbeat. Finally, the multiphysics was applied, allowing the two types of physics to interact and have effect on one another, with pressure from the blood deforming the artery wall and stent. In taking this approach, we would be able to model and understand the coupled behavior of fluid and structure, increasing our knowledge of how stents behave in real physiological conditions.
With the base model established, we then explored how changes in the material and geometry affected the performance. We created 3 variations of the stent design. The first was the original model, which was served as our baseline. The second involved changing material to titanium, allowing us to evaluate how increased stiffness influences deformation and stress distribution. I then altered the geometry on the model we found and chose to use. I increased the radius and the length to cater for different patients with different artery sizes, for men and women, different ages, observing how stress and blood flow were affected. The third variation focused on geometry. We modified the mesh structure by adjusting features such as slot length and spacing to improve flexibility and reduce obstruction to flow. Lastly, I created our own stent with simple geometry to test more materials and stiffness and how they compare with other materials under similar stress conditions. These other materials included steel alloys and chromium. Each model was tested under identical conditions, including the same blood pressure, flow rate, and arterial properties, ensuring a fair comparison. We evaluated performance based on 2 key criteria. First, how smoothly blood flows through the artery, which relates to friction and flow disruption, and second, how the stent deforms under pressure, which reflects its ability to mimic the elasticity of a natural artery without causing damage, and how it responds to plaque. By isolating material geometry as variables, we were able to directly assess how each design choice impacts overall performance. We found that the model of the steel alloy and more elongated geometry performed the best. It had the least friction with the blood flow, and it had elasticity more similar to the natural artery than titanium model did. It was far too stiff. The larger geometry also outperformed the original without even the change in material.
In concluding our multiphysics stage of our product research, we found that an effective stent is more impacted by geometry than it is by material, as geometry is what allows for artery-resembling structure, flexibility, radial strength. We also discovered that in order to minimize friction and achieve the ideal amounts of elasticity and flexibility, overly stiff materials were simply not sufficient. Now, the moment we've all been waiting for, our final product. Introducing the Arterial Stent Reimagined. Our design consists of a highly effective stent design that has optimized geometry and material selection based on the previously stated criteria, which in turn produced a closely artery-resembling stent that has reduced flow disruption and arterial stress, showcasing a never-done-before stent that only rivals the real thing. The impact this will have is that cardiovascular healthcare, as we know it, will become more pro-patient. This newly improved stent will lead to reduced clotting risk measured by our flow metrics, a longer stent lifespan measured by our stress strain metrics, and improved patient outcome. However, while our model captures key fluid and structural interactions, it does not account for long-term biological responses such as plaque buildup, inflammation, or tissue growth. We also use simplified material models that do not fully represent the nonlinear and time-dependent behavior of real biological tissue. This model does not fully consider the both physical and non-physical activity baseline heart rates for stent patients, as it was modeled based on the average resting heart rate for stent patients. Our results are not directly validated against experimental data, which means they should be interpreted as comparative rather than predictive. However, with more funding, your funding, we intend to address these limitations. Future work would involve expanding the model within COMSOL to include non-Newtonian blood behavior, more realistic vascular geometries derived from medical imaging, and advanced material models for arterial tissue, as well as including various parametric sweeps to consider all the heart rates valid within the non-physical and physical ranges, as well as heart rates outside those ranges to consider performance in situations where the patient may be experiencing complications or severe physiological conditions. This would also indicate future developments of our stent that could possibly be used to detect stent thrombosis and other conditions, hence giving us a possibility to branch out into predictive healthcare. Invest in Arterix, invest in health. Thank you for watching our pitch. I'm not reading the next line, but you know what to do.